Hey everyone, welcome to my first video on flight test. Part of what I do for a living is flight test new airplanes or modifications to existing airplanes. I have worked in flight tests for many years, flying experimental airplanes and running them through test programs for certification. I am a member of the Society of Experimental Test Pilots, and that has given me access to a lot of useful information, specifically papers and videos on flight test programs, experiences and lessons learned from other test pilots and organizations. This hopefully keeps me from making the same mistakes that others have made. Flight testing new things is risky, and we need to minimize the chance that things go wrong. Unfortunately, these lessons learned are not shared with the public, and to understand them, one already has to have a strong background in flight test. There does not seem to be much publicly available information on flight testing that is useful and easy to understand. Pilots and aircraft homebuilders are mostly on their own, even though many of them perform flight tests of modified or newly built airplanes. I want to use what will hopefully become a series of flight test videos to share some of the lessons learned in the form of examples. In this video, I want to introduce you to flight test planning and use a change I made to my Pulsar elevator trim system as an example for a simple test. This is what I will talk about: the system's overview, test points, ground and flight tests, test card examples, additional test points for more complex trim systems, a hazard analysis, and test results and lessons learned. The highest priority in flight test is safety. It starts with a review of the system I am about to test. I want to be completely familiar with the modification so that I know how it works, how it is operated, what its limitations are, and to get an idea what potential problems may come up with it. Here's an overview of the system. In this case, it is a simple mechanical spring trim system. Because I designed and built it, I'm already familiar with it, but I still look over the components again. It consists of a knob in the center console, which is connected to a cable. The cable is routed through a guide back to behind the seats and is attached to a spring. The spring is attached to the elevator control tube with a clamp. A second spring is attached on one end to the same clamp and to a bulkhead at the other end. In flight, in the balanced state, the stick remains in one position with no force on it. This is the trim speed. If the knob is turned, it moves in or out. The cable is either pulled or relaxed so that the spring it is attached to either pulls the control tube in one direction or allows the second spring to pull it in the opposite direction. The changes I made to the system were an adjustment of the location of the guide attachment and the clamp location. This means that the trim range has changed, and I need to find out if this is okay. So what needs to be checked before flight? Several things come to mind. First of all, does the elevator still have its full travel up and down? Nothing should rub or bind or restrict the travel. What are the test points? The purpose of the trim is to eliminate the stick forces for all steady flight conditions in a certain speed range. What is the speed range? Since this is an experimental airplane, this is up to me, but I want the trim to cover all speeds that I would maintain for a while, which means from climb to cruise to descent and approach. I do not need to be able to trim it all the way down to stall speed, nor do I care to trim it at VNE, so that can be excluded. It also needs to cover the whole CG range that I can fly at. This gives me a few critical points to verify. I need to have enough up elevator trim at forward CG for slow flight and enough down elevator trim in high-speed cruise. The elevator deflections at aft CG are smaller because of the reduced stability, so there I will only check that I have enough down elevator trim at high speed. Because the pitching moments and therefore elevator deflections for steady flight change with flap deflections, I also need to verify that there is sufficient trim authority for all flap settings up to the maximum flap speed. The requirements I have just listed are basically what can be found in the airworthiness requirements for certified airplanes, In paragraph 23.161 of 14 CFR Part 23. It lists a trim speed range from 1.4 times stall speed flaps up to VH, which is the maximum level flight speed. Power changes can also affect longitudinal trim, so I will take that into account. With this information, I can fill out a test card with the points of the speed and configuration envelope I need to check. This shows the prepared test card with room for information about the airplane, pilot, configuration, location, and weather conditions on the test day. The test card is a piece of paper which I take with me on the flight, where I check off the test points that I have flown in this matrix. I document if it met the requirements or not, and record any additional data such as speeds reached and any issues found. The test card matrix is a reminder to me in flight which points need to be checked. For example, the first line that reads VH up level refers to the speed, the flap setting, and that it is to be flown in level flight. The power is set as needed for the speed requirement, which is full throttle here. If something other than level flight is required, the power is set as listed or to meet the descent rate. Once I have completed my test cards and have not found any issues, I can declare that the trim system changes were successful. If this was a completely new trim system, the list of things to test would be a bit longer. For example, I would want to check what the control forces are if the trim is at the limit. Can the airplane be safely flown if the trim is fully forward, or would that exceed the pilot's strength? Same for the trim in the full aft position. It is not too critical for an airplane as small as the Pulsar, but with its short center stick, the forces can become unpleasant if the trim is not in the right position for takeoff. Every trim needs to have a means to indicate its position. This requirement is fulfilled here by the knob itself and how far it protrudes. Another consideration is particular to this airplane and installation. If the knob is fully out or aft, does the stick contact it? If it is fully forward, in this case, it still has clearance. If the trim is electrical, you have a more complex system. Check as much as you can on the ground before flight. If there are two sticks or yokes and both have a trim button, check that they both work. That they both work in the same direction and in the correct direction. Verify that the trim position indicator is at one end when the trim or trim tab is also at its stop. Something that can only be evaluated in flight is the trim operating speed. While in my case the trim operating speed is limited by how fast I can turn the knob, an electric trim system that runs too fast or too slow can increase the pilot workload, which is undesirable. With the system information and this list, I can now perform a flight test hazard analysis. With only one system to test, this list is pretty short. Basically, this means asking yourself about what can go wrong with the system or with the flying part. Break this up into what is the effect of the failure, the probability of its happening, and as a result, what the risk of the test is. Look at the causes, how to deal with the effects, and how to prevent them from happening in the first place. I came up with these points for the trim system, although only the first 3 apply to the Pulsar. The trim range setup is wrong and it may not be possible to trim the airplane in all the test points. This can result in high stick forces at some speeds and increased pilot workload. Once the pilot realizes this, he should abort the flight, make an adjustment and try again. So 2. Trim is not moving or jammed. The result is that the airplane is mistrimmed except at one speed. The stick forces can be high, pilot workload increases because one hand has to stay on the stick. If this should happen, the flight is aborted. With a mechanical system, checking that it works on the ground should assure that it also works in flight. An electrical trim system can stop working if a wire breaks or something shorts out. If this happens, it is considered more annoying than hazardous, and the pilot can still fly the airplane with some stick forces. I have seen this issue on a maintenance test flight, where the mechanic forgot to reconnect the trim wires after reinstalling the stick. 3. The cable or a spring breaks. This is a more serious system failure of a spring trim system because it suddenly increases the force on the stick. If the pilot does not have his hand on the stick and reacts right away, the airplane may pitch up or down suddenly. This can cause an unusual attitude and at high speed, in an extreme case, can overstress the airframe. Trim parts are more likely to break when they are worn, so a new system is much less likely to fail than a 50-year-old system. To minimize the risk of this happening, inspect the parts annually and replace them if any wear is noticed. This is not just a flight test hazard, but can happen during any flight. The likeliness that this happens is fairly remote though. With an electrical trim, there is the possibility of a trim runaway. If this is noticed, the pilot should deactivate the trim by quickly pulling the circuit breaker. Stick forces are increasing during the event. Here it is helpful to have a fairly slow trim operation speed to give the pilot time to react and to keep this event from becoming hazardous. If this happens in combination with autopilot operation, it may not become obvious until the autopilot cannot overcome the trim force anymore and disconnects. This can cause the airplane to suddenly pitch up or down and has caused accidents in the past. The system should provide a warning to the pilot to indicate that something is wrong. The trim runaway test is the only one that should be considered medium risk because of the chance of rapid pitching of the airplane. 5. If the elevator has a trim tab, a linkage to the tab can break. This has also caused accidents in the past on those airplanes that had no redundancy. Therefore, certified airplanes are required to have dual actuators or some other form of redundancy, because a loose trim tab can easily cause flutter. On airplanes with a single linkage, consider adding a damper or friction device that prevents the tab from moving rapidly. To decide if a certain flight test is low, medium or high risk, run the potential failures, issues or difficulties with flying the test points through this matrix. If, for example, a failure has only a minor effect on the operation of the airplane and the probability of it happening is remote, the test is low risk. If, on the other hand, the failure has a major or hazardous consequence and its probability is probable, the test is high risk and requires some thought on how to reduce the risk for the crew and airplane. This could mean using extra safety equipment like a parachute and using mitigation procedures such as performing the tests within gliding range of a runway. Using my own judgment, I decided that my trim system tests are low risk. With all this preparation work done, I can go fly. The flying part is easier than the preparation. The test points are well within the capabilities of all pilots. You can try this yourself in the airplane you normally fly. The result in the pulsar was that the trim worked fine at forward CG, but at aft CG I did not have a sufficient forward travel of the knob and too much travel aft. I made an adjustment and flew again. Any adjustment invalidates the previously flown test points, so I repeated the tests I already flew. In the end, I found that the trim worked satisfactory. Lessons learned: be familiar with the system you test. Even though a test may be easy to fly, it may not work the way you expected. Be prepared for system failures, however remote they may seem. Think about what can happen beforehand and have a plan B. I hope you found this video useful. Please subscribe if you want to get notified when the next video is ready.